Hello everyone. Now that we have finished analyzing the system using the body diagrams and Nyquist plots in the frequency domain, we are ready to start designing the controllers in the frequency domain. We will do it mainly using the body diagrams, and here we will see the general procedure first. So here we have the general concepts. Using the body diagrams, we will design the controllers, just as we were doing it with the root locus approach, but there are differences here now. With the body diagrams, we can synthesize controllers for stable open loop systems, or open loop systems where there are no poles in the right half plane. While with the root locus approach, we didn't have these limitations. So this is one limitation that we have in designing the controllers using the body diagrams. However, on the other hand, we can now consider the attenuation of the process disturbance and noise. We have seen in the analyzing of the system, closed loop system using the body plot already, that we can talk about the amount in which the disturbance, process disturbance, or the noise, sensor noise, could be attenuated for a given frequency range. And we can discuss about this by referring to the amplitude plot of L of J omega. Okay, so this is something that we didn't have in designing the controllers using the root locus approach. So this is indeed kind of it shows somehow the strength of the designing controller using the body diagram. So these two are the main differences that we have in terms of the capabilities of the controller design. In order to start designing the controller, we will write down GP in the body form. GP is the process or the plant. We will write it in the body form, and the body form is like this. We will have the generalized gain GP tilde over S to the power of HP, where HP will give us the type of the system, times the first order zeros multiplied by each other divided by the first order poles multiplied by each other, 1 plus STJ or 1 plus S tau I, and then we will multiply them with the second order zeros divided by the second order poles. So you can see that for this part, if you replace S with 0, we will obtain 1. So if S is set to 0, then for the whole thing here we will get 1. GP tilde is the generalized gain, and HP again shows the type of the system. We can similarly show the controller GC of S in the body form. We will have GC tilde as the generalized controller gain, S to the power of HC, where HC is the controller type, times the first order and second order zeros and the poles of the controller. Then, depending on the structure of the controller, GC of S, we can obtain different controllers could be indeed realized. Yeah? The different types of the controllers that we have would be, we will start with indeed a proportional controller, where we will have GC of S will be equal to GC tilde. So this will be the simplest controller, yeah? And you should know that the effect of this controller would be to move the amplitude plot up or down. If the proportional controller isn't enough, we will have the first order controller. And the special cases for the first order controllers are PI, lag, lead as the practical ones, and the PD controller as the ideal one. So PD is also a controller, but it is not the ideal PD is not practical or realizable. Then the next kind of controllers that we have would be the second order controllers. In the case of second order controllers, there will be 2 poles at the denominator of the controller. Then the special cases are the practical PID controllers, lead lag compensators, and the notch filters. These are the particular cases, but these are not a limitation. So depending on the situation, you might end up by designing a controller which has a single pole, for example, yeah? Or it might have, again, it would depend. It might not be a lead or lag, but still first order controller. So these are special cases that we will consider, but then again, depending on the situation, you may come up with a controller which is not any of the ones that we have listed here. You can also come up with a designing of a controller which is of a higher order, be higher than 2 in it. The order is higher than 2 if required, but you should keep in mind always that it's the best is to have the simplest controller design. So that's why we will start with the proportional one and then consider the first order controller, then the second order, and if needed you go further. Now let's have a look at the requirements. As for the requirements, we will check them directly using the transfer function that we have for the loop, L of S or L of j omega, in the form of GC of S times GP of S. And we will have it in the body form as well. So this is the body form for L of S. Regarding the closed loop stability, under the assumptions that we had for applying the body principle, the closed loop system will be stable if the phase margin is bigger than 0. But we should keep in mind that we have made some assumptions to have this functional. If phase margin becomes bigger than 0, our system will be stable. If it's smaller than 0, the system will become unstable. And in some cases, we might need to have some degree of robustness. In that case, instead of saying phase margin should be bigger than 0, we will have a given threshold for the phase margin. For example, phase margin should be bigger than 30 degrees. Or we can also have the gain margin being used as a robustness indicator. Instead of saying gain margin should be bigger than 0, we might say gain margin should be bigger than 10, for example. So that those will give us some degree of robustness. In terms of the steady state behavior or steady state error for the polynomial reference or disturbance inputs, we know that it will depend on the generalized gain and the type of the system. So these two will be responsible for the steady state behavior. Having that in mind, we can decompose the controller GC into 2 parts, GC1 times GC2, where GC1 is composed of the generalized gain over S to the power of HC, and GC2 includes the poles and zeros of the controller. And now we see that for the steady state behavior, only GC1 would be responsible, and if you have requirement in terms of the steady state behavior, we will focus on designing the GC1 part. GC2 part will be used for the transient behavior. When we talk about the transient behavior, we should indeed consider how the transient step response parameters are related to the body plot of the L of j omega. One thing to consider is that a possible indicator of the speed of the closed loop system in tracking the time varying reference is omega c. The crossover frequency is an indication of the speed of the closed loop system. So if you want to have a fast, let's say, response for your closed loop system, the omega c should be big. It's also related to the bandwidth of the closed loop system's transfer function, T of S. We also know that given requests on step response parameters, such as settling time and overshoot, we can approximately find some values for the omega c and the phase margin. So depending on how much settling time and overshoot is required, we can find the desirable values for the omega c and phase margin, and then in designing the controller we try to achieve them. And therefore, once we have GC1 defined based on the steady state requirements, we can focus on finding the proper or forming the proper omega c and phase margin in order to satisfy the transient requirements. Regarding the attenuation of the effect of unknown inputs, the disturbance and the noise in particular, we should have a look at the amplitude plot at the low frequencies for the disturbance and high frequencies for the noise, and the amplitude plot for L of j omega should not enter the forbidden areas or the dangerous zones. If it enters into those areas, we need to modify the amplitude plot for that range of frequencies in order to take the amplitude curve out of that forbidden zone. And we might need to check it for GC1, the first part of the controller, for the disturbance especially, because this happens at the low frequency. And for the noise, we need to have a look at the high frequency part. In terms of controller realizability, we know that in order to have the controller realizable, the number of zeros shouldn't be more than the number of the poles for the controller in the transfer function. So otherwise it will be an ideal one which will not be realizable. So we will focus mostly on the realizable controllers, which will be the proportional PI, lead lag, practical PID, and the lead lag compensators for now. So in general, you should keep in mind that if you want to have the controller realizable, it should be a proper or strictly proper transfer function. Alright, so now that we have all these in mind, we will start to see how we can design the controllers in the next video. We will start with the first order controllers for minimum phase systems, then we will have a look at the second order controllers, and then for the minimum phase systems, then we will have a look at the non-minimum phase systems to see how the controllers could be designed for those kind of systems. That's all for this video. Thank you for watching and see you in the next video soon.